All right, so we're going to go ahead and get started. This is our last seminar for the year in the semester as part of the AI-SDM seminar series. Today, I'm happy to welcome Dr. Ann Bostrom, who holds a professorship, an endowed professorship in environmental policy in the Evans School of Public Policy and Governance at the University of Washington. She's also involved and heads up a couple of NSF-funded initiatives. She's the co-director and co-PI of Cascadia Coastlines and People's Hazards Research Hub, and a co-lead in one of our sister institutes in risk communication with the AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography, AI2ES. So welcome, and looking forward to your talk.
Thank you, Norman. So please, I'm sorry to stand between you and your exams and you and the holidays, but I'm really glad that you have lunch and I'm just the lunchtime entertainment, and my regrets to those of you who are online and aren't having lunch for free. I'm very pleased to be here today to talk about and converging on trustworthy AI for weather, climate, and coastal oceanography through risk communication. And you'll see here the roots of this work in my own previous work at Carnegie Mellon. So very happy to tie that connection. If I start speaking too quickly or you can't hear me, please just flag me down. So, and I will stop. So you'll see on the slide here, not just me, but a large group of people. And these are part of the evolving risk communication research team at AI2ES. And the Institute is now in a no-cost extension year, so we've completed our first 5 years of funding. We do have a couple of other small pots of funding, but we were not renewed by NSF. So the work is winding down. And so several of these people on the slide have graduated or gone on to other positions. And in fact, most of the people on the right-hand side. So let's see if I can get this to work. So it brought together scientists from a number of different disciplines to work on these problems. And you can see here an equation that we developed to explain what we do in the AI Institute. Is this big enough for you to see this? You can see here, this is risk communication, trustworthy AI. So this is AI developers primarily. Environmental science, this is convective hazards, winter weather, coastal environment and tropical cyclones, as well as S2S. We didn't ever quite get to the S2S part, seasonal and subseasonal forecasting, but there's been a lot of work on these other domains over the course of the Institute. And the risk communication group had as its goals to address foundational and interdisciplinary risk communication problems and conduct research in AI for weather hazards to identify factors that influence trust in AI for professional user groups. And we focused on professional user groups specifically because they are people who are using the model. So they're not model developers typically, though they may be working with model developers, and they are influencing a very large audience. We find people like weather forecasters, emergency managers, their interpretation of the models and their conveyance of what the models are saying affects most of society. So it's it's what we're trying to leverage that critical position that they hold. We also wanted to determine how AI trustworthiness influences risk perception and use of AI by these professional users, and then through them, all of society, and inform the development of trustworthy AI approaches to improve decision-making and their decision-making about messaging, among other things. So this is the roadmap of the talk that I'm going to give. And you can see there are 4 pieces here. The first is I'll talk a little bit about how risk communication AI2ES, where it fits into the general picture and exemplifies convergent user-centered research for the development of responsible and trustworthy AI. Then I'll talk specifically about our research approach in the second piece. And then the third piece, I'm going to give you a case study example, our work on severe convective weather models. And then finally, I'll wrap up with some of our findings across scales. So before we began our specific case study work, we, in the very first years of the Institute, held a workshop that influenced all of our work subsequently. And this workshop brought in a number of people, about 29, I think it was, 30, in a virtual environment. It was the beginning of COVID, to look at a research agenda on AI, in AI for the environmental sciences. We brought in people who are AI developers. We brought in several of the key people from our own AI institute, but also people who had been working on trust in AI and on AI, modeling trust in AI, such as Robert Hoffman and his colleagues, and thinking about what it means to use AI and how people respond to it. So many influential people, as you can see here. Well, you can't really see all their names, but if you look at it, it's a long list of authors who are all members of the workshop, and how they were thinking about this, how they developed an understanding of how to study it. And everybody wrote issue papers that contributed to this collective paper that summarizes it. And the research agenda has these four key points: better ways of measuring trust in AI as a dynamic process, contingent process, better understanding of which contingencies and contextual factors actually matter in people's understanding of AI, how to think about standards and calibrations of trust, which we concluded deserve close scrutiny and a more empirical evaluation. There's a lot of push for calibration of these kinds of things, and it's not clear exactly how you do that. And finally, to integrate knowledge learned in risk and uncertainty communication in studies of trust. And there's a long history of studying trust and risk communication, and it plays a pivotal role in that. We hoped that our studies that we subsequently conducted would address some of these factors, and they are intended to do so. That paper came out in Risk Analysis last year. And subsequently, we have a paper that's come out called Reconceptualization of Trustworthy AI, that was led by one of the postdocs who we hired, Chris Wurz, who's now a faculty member at University of Illinois Urbana-Champaign. And this paper pulls, especially in the organizational studies and the social science studies that have been looked at trust initially. And so it concludes that trust is subjective, contextual, and dependent, and that it should be treated as something that, like risk perception, is very much personally driven for the individuals who are doing the assessment. And that subjective assessment has to be paid attention to. This is not a popular view among the AI developers, who would really like to just have a set of equations that they can use to apply to decide when their model is trustworthy. So I just to set up a little bit further of this framework, I'm going to give you a few definitions. First, from Ortwin Wren, who's very well known in the risk perception literature, and I wasn't sure if I'd be preaching to the converted here. How many of you have a background in risk? All the people I know in the room. So risk has a lot of definitions, and Brooke Fischoff wrote a very nice paper illustrating the power dynamics and who defines risk. And this plays a big role in government work, in particular, where risk standards are set. It matters who defines it. Ortwin Wren defined it as a possibility that an undesirable state or adverse effects may occur as a result of natural events or human activities. And hazardous weather exemplifies this, especially extreme hazardous weather, as you can see pictures of here. The use of the term risk, some people have argued, in the increasing volume of interdisciplinary literature is so heterogeneous that some authors even argue there are hardly any connections at all. So it's a very broad term, and bear that in mind, because this relates directly to how people interpret when they're going to trust something. Risk assessment, as defined by the Society for Risk Analysis, are approaches and methods for identifying risk sources, threats, and hazards, and understanding how they can occur and what could be effects, and representing and expressing the risks and uncertainties. And risk assessments are often conducted and usually necessary for designing risk messages. Risk perceptions, we argue, should also be considered that way. This also comes from Ortwin Wren. We think of risk perceptions as subjective risk assessments. So if you think of that definition of assessment, people do this subjectively and intuitively anytime they encounter a risky situation. And he pointed out that there are 4 different levels of, Ortwin Wren and Rorman actually identified 4 context levels for risk perceptions and unpacked how multidimensional risk perceptions really are. So the individual risk perceptions are shaped by information processing heuristics such as those studied in social and decision sciences here at Carnegie Mellon. And they're also affected by cognitive factors like prior beliefs, Stigma is a big factor, especially we see stigma now emerging, I would argue, I don't know if there have been that many studies of it yet, around AI because of the energy intensity of AI model development in particular, but also emotions and affect. And so when you talk to people and they have a reaction to AI, even if we're talking about machine learning in technical contexts like weather forecasting, people seem to have an emotional reaction that has to do with their experience, their personal experience, or their anticipated experience with large language models. So there's a certain halo effect there. Risk perceptions and so consequently subjective risk assessments are also affected by social values, trust, and economic and political institutions, which play key roles in risk perception and communication as well. Climate change perceptions, for example, became politically polarized. And while a greater than ever proportion of the US, believe it or not, despite the administration, see climate change as important, and neither identify as conservative nor liberal. If you're survey methodologists, you'll know that it's like 40% of people will put themselves in the middle of that scale or not identify themselves on that scale. Polarization, nevertheless, at the extremes on climate change has increased, and we see that continuing over decades. Finally, at the top level, cultural institutions, social norms, identities, worldviews, these all shape risk perceptions as well. Across all levels, there are both collective and personal contextual factors shaping risk perception, and so consequently shaping trust and the trustworthiness that people assign or attribute to a specific technology like AI. And you can see here this very broad definition of risk perception that Nick Pigeon gives that is much broader than what we saw from Wren and Worman. So risk messages are an outcome of all of this and another design factor. And so those are defined by the National Research Council in 1989 in their report on risk communication as information about the potential threat, severity, consequences, or recommended actions from hazards. And you can see here the cone of uncertainty on the left, which can be considered as a risk message. And other information products shown here are also risk messages coming from extreme weather events. So this is the context that we're thinking about AI modeling in. And in the weather context, this is where our risk communication at AI2ES fits, right in the middle in the risk assessment, subjective risk assessment piece here. For weather forecasters and other experts and professionals like emergency managers or Department of Transportation officials, AI/ML guidance is a form of information that they use to assess risk and to issue risk messages. So it's a risk message itself, and it is used to craft risk messages. So now I'm on the second piece, which is more our specific framework for the work that we've conducted in AI2ES. The guiding tenets of our research are basically three big points. First, that AI, ML, and other model guidance is a form of risk information for expert users that they use to assess and communicate about risk and environmental hazards in particular. And so by professional users, we mean all kinds of people, weather forecasters, emergency managers, transportation officials, people working on oil rigs, for example, are also, and fisheries. User engagement, in the second point, is essential to effective risk communication, including to develop effective risk information. And this is something that social and decision scientists here at Carnegie Mellon have recognized for decades. And there's a quote from Julie DeMuth, my co-lead on risk communication at AI2ES, illustrating this for forecasters. And third, conducting convergent research that cuts across sectors and disciplines and is problem-focused is the goal. Integration of knowledge, data, and ideas through co-development, co-analysis, and co-interpretation of the information to address compelling problems. So here's our framework that we started with and that we're still sort of using. So you can see here that we have use cases at the top. And so these are specific hazard use cases, most of which are associated with extreme weather, but also ocean loop current eddies we looked at as well, forecasting those. And I'm going to talk today about one of these use cases, severe convective, and it's with two different models. And we have an interdisciplinary research team. The risk communication team itself is actually interdisciplinary in its own right, with people from political science, from environmental policy, from risk communication, and from meteorology. But we also work very closely with the other scientists in the AI Institute, who are both atmospheric scientists and AI machine learning scientists and developers. So a very, it's been done already?
Sorry.
Yes. We have a variety of social science methods that we propose to use, including semi-structured interviews, and there's a lot more to say about that I will say, randomized experiments, and then ultimately surveys in naturalistic settings that we wanted to conduct longitudinally, and we haven't gotten to that yet, and I hope we will before our funding completely runs out. I'm working with a variety of decision makers shown here on the right, that, as I already spoke about, and then looking not only at machine learning, but also techniques, but also explainable AI techniques. And this we hope would lead us to an ability to say more about what it is that makes AI trustworthy. So finally, I will dive into the specific use case, which will, yes.
Don't most users of like weather or information, you get on your phone and you get some information, and it might have been generated by AI, or it might have been generated by experts not using AI or machine learning or whatever. Isn't that the vast majority of cases, that people have no idea of whether and to what extent and how AI was involved in the information that they're receiving?
Well, let me take it a step further. There's been some interest in whether people value the National Weather Service, and it's been pointed out. It's been argued by some federal officials that they didn't think that we needed government to get involved in this. After all, we have AccuWeather, for example, and the Weather Channel. Why do we need the government? So it turned out that they didn't know that the source of all the data for all of those forecasts is the federal government. Government resources. And so there was no distinction between data and forecasting that came from the National Weather Service versus NOAA versus AccuWeather and Weather Channel and others who are just post-processing basically that information. So yes, but that is exactly why we're focusing on professional users who actually interact directly with the models, and they design all of that weather forecast and warning information based on their interactions with the models. So it's our proposition that the design of the specific model is more likely to influence, and is probably only likely to influence, those kinds of professional users who are interacting with in conventional numerical weather models or with AI weather models, and may notice the difference. Even they may not notice the difference, but that was something that we wanted to research and investigate it. And you could argue that is actually changing dynamically over the time period of the institute that we had. So yes, but not relevant to what we're doing here directly.
But also formal warnings and evacuations are always from an expert user.
Yes, exactly.
So in that vein, what exactly is meant by AI? So when you started,
let me give you a concrete example here. So that is changing over time too.
Right.
So very rapidly. So I'm going to talk about this case study here, and I'll go back to your question in just a second. So I want to say first that this is a paper that has come out. It came out last year, exploring National Weather Service forecasters' assessments of AI-guided trustworthiness. The paper was led by Mariana Keynes, who's a postdoc and now has another position at the National Center for Atmospheric Research in the RADS group, Weather Risk and Decisions in Society. But I want to just point out that Mariana worked very closely with all of us, and Julie and I actually worked with other scientists in AI2ES to develop the initial methodology for this study before the postdocs even came on. So very much a group effort, and the people on the right all worked on helping analyze the data as well as collect the data. So, but Mariana deserves all the credit for most of the slides that I'm going to show you. She's got a real knack for doing visuals, which I hope you'll appreciate. And I'm going to focus on the social semi-structured interview part, and specifically among decision makers, the National Weather Service forecasters and a variety of forecasters. We have two general research questions. First, how do forecasters decide what model guidance and other tools to use in their operational forecasting process? So we had found in a previous study where we were looking at the hurricane, tropical cyclone forecast and warning system in the US, that there was proliferation of products that forecasters could use. In fact, we had a list of like, I don't know, some 30 or 40 products related to hurricane forecasting. And most of the people who we interviewed, who were all professionals interacting with the forecast and warning system, broadcasters, forecasters, emergency managers, only knew a few of the products. And so selecting among products is not a small task. And those people who work in the forecast offices are faced with this giant set of tools that they can use to in their forecasting process, and they have to decide among them. The second question is, how do different descriptive and performance attributes of prototype model guidance developed using AI influence forecasters' assessments of guidance trustworthiness? And this came up in the workshop. People had lots of theories about what it is that's driving this, and so we had some hypotheses going into that. And so this is a user-centered approach to developing AI guidance, and we felt that this would give us an ability to address prototypes, models that were being developed in AI2ES for extreme weather events in particular, but also loop current eddies, for example, and that we could then influence the development of those models and people's understanding of whether the models were ready for operational use. So the first part is looking at that forecast, the AI, selecting and looking at AI or machine learning derived forecast guidance. The models that we looked at, I'll show you that is a random forest model, convolutional neural network. So they're very specific models. These days, there are a wide variety of different kinds of model architectures, and then there are the purely data-driven models that are a whole nother ball of wax, I'm going to say. So they're a very different proposition, and don't have the same kind of identifiable structure. So I'll start with those two prototypes, and I hope that addressed your question about what I mean by AI in this context. That said, we have an appreciation that both these professional users and the broader audience that George mentioned may not make any distinctions if we say AI or even machine learning. We'll talk about the interview protocol, the interviews that we conducted, the transcripts that were derived from those, and content analysis of those. And the idea here is that this is, as I mentioned, an iterative cycle that we were hoping to influence, if not the development of those specific prototypes, but the development of future prototypes for extreme weather forecasting. And I will highlight the methods for these storm mode and hail, which are the two severe convective models that we'll be focusing on today. The storm mode is a convolutional neural net model predicting the probability of storm mode, supercell, QLCS, disorganized, and that was developed by Ryan Sobash as the primary lead on that development. The hail is a random forest model predicting the probability of hail, and one of the things that was noted at the time is, first of all, storm mode was still identified largely by hand, and hail, there have been some attempts to predict that, but hail is hard to predict, and extreme hail is becoming more common, as you may or may not know. And extreme hail can be extremely damaging. And we found that the insurance industry, among all the climate change risks that have caught their attention, are the increases in these severe hail events where you have greater than 1 inch diameter hail that can actually cause infrastructure damage and that kind of thing. So these are both models that were prototypes that were identified to address societally relevant and important hazards and risks. We conducted one-on-one interviews with 16 National Weather Service forecasters from central, southern, and eastern regions. Those regions were selected because of their predisposition to these kinds of weather events. And the median experience was 16 years, so quite experienced forecasters on average. 7 general schedule, 12 meteorologists, 4 lead meteorologists, and 5 science and operations officers or SUs. 9 of these, so we did randomly assign them to one or the other of these use cases. 9 reviewed the probability of storm mode model, and 7 reviewed the probability of severe hail model. And these were conducted a few years ago. And so like one thing I want to just comment on is there are some mismatches between our methodology and the speed with which AI is developing. So, which we became aware of acutely during the timeframe. Okay, so this is the general. I'll move on to the interviews here, and you can see that it's quite a complicated architecture here. We started with pre-interview surveys. We wanted to find out what people thought before we talked with them or had them involved in the work. And so I'll talk about that first. And then I'll go on and talk about the detail of these virtual interviews that have quite a few different components, including a look at, so the structure of the whole interview instrument is the forecast challenges and informational needs first, to identify opportunities to develop new AI ML guidance, perceptions of and attitudes towards AI and AI trustworthiness in general, and then perceptions and feedback about AI forecast guidance. And then we went into a think aloud, which is a technique that was developed here at Carnegie Mellon between Herb Simon and Anders Ericsson many, many years ago. And I'll talk a little bit more about that. So first, the pre-interview surveys. So we ask first in these pre-interview surveys, which were written surveys basically, we ask forecasters to think about an actual severe convective event during the pre-interview survey. This approach, it takes inspiration from critical incident technique, which results in more detailed and contextually relevant answers. So if you get people to focus on a critical incident that's salient in their mind and they can think about the characteristics of it accurately. And that gives us contextually relevant responses. The 20 survey items that we had were inspired by all the previous research that we'd heard about and read about building up to the workshop, and in the course of the workshop learned about. And so this included questions about AI explainability, interpretability, transparency, and performance, and the details of performance. And we actually tailored these questions quite a bit and expanded the survey to focus on severe weather forecasting based on our prior work with the forecast and warning system, among others. And Julie DeMuth has led quite a few studies on severe weather and continues to do so. So now to the meat of the, yes.
Could you just quickly say a little bit about what the two, you had the operationally relevant things and the training?
Oh, yeah. So when a new model is introduced to the National Weather Service forecasters, they get some kind of familiarization or training with it. And so we anticipated that they might have different needs at that point where they're being introduced to a model for the first time, as opposed to operationally where they would have certain kinds of requirements for the model. So like, among other things, if they have a model that's not accessible all the time, so these are high bandwidth and sometimes difficult to access models, or they have been in the past at least, and all numerical weather models can be that way. And so that there might be something that they would demand or want in an operational setting that they wouldn't need in the training, and vice versa. So we wondered if these would be different, and you'll see in the results that they do differ a little bit. So yeah, and we also had a lot of discussions about the response scale on this, because we were trying to keep this short and so we wouldn't get dropouts and wouldn't overburden our respondents. National Weather Service forecasters have become a target of opportunity for people in this kind of research. And so they've been overburdened. And Julie was trying to maintain her good relationships with the National Weather Service. So we tried to keep it short, and we ended up with a 3-point scale, which I do not think was enough. I think we should have had 5 points on the scale at least, but we thought that was a sort of a minimal scale, and Robert Hoffman had used that with some success. And anyway, so the scale goes from that it's essential to have that, would be useful, but not necessary, and then not necessary. So do we really need this feature or not? So for example, do we need to be able to sample the product and see the inputs that yield the output? Do we need to be able to examine the guidance predictions for past or archived cases, and before we decide that we can trust it? Okay, so let me dive into the virtual interviews themselves. Have this long structure that okay, so the interview structure, after those general questions that I mentioned, we dive into this think aloud approach where forecasters verbally shared what was going on in their minds. We asked them to just say what was passing through their mind without explaining. And you'll see from the quotes that this was not necessarily 100% effective. We do give people a little practice exercise on this, but there's a lot of discussion about whether think alouds are different than other kinds of survey responses or not. Are you really getting what's going through people's mind, or are you getting something that they're fabricating to explain to you what's going on or what they think you want to hear? So we started by giving them background information on the models themselves. So for the Hale guidance, you can see the kind of picture that they get. They get a couple of pictures of outputs from the model, and they get a general description of the model architecture. So, after that, then we asked them to work through this board. And this is an information board and it has 6 stickies at the bottom. And so they're given a task. So this is built actually on the mouse lab studies. That was the inspiration behind them, which Eric Johnson and others conducted. We didn't have anything to unveil, but it is kind of an unveiling, because they click on any one of these stickies and they're taken to a set of information that corresponds to that. So the detailed information behind that. And so we had this informational board with sticky notes for the 6 attributes. And you can see on the left here, it says that they're asked to see whether or not this will affect their trust of the model. And so it either decreases on the left, has no effect, or increases their trust in the model, basically, or the trustworthiness of the model. And we're asking them to think about as they're doing this. So the idea being that we'll get some insight into what it is that's actually driving their judgments of trustworthiness. And then the slides, you have a thumbnail here in the middle of the slides containing the text and graphical information for the 6 here. You can see those are actually pictures of the slides themselves, but we had to work with the modelers for months to develop this information, because it needed to be realistic enough to be able to be the sort of thing they would get in training. It had to be accurate, and it had accurately described the models. And then we ended up with a sorted board where they had put all the stickies on one of the squares. So a little bit on the results of the first. Oops, okay, so pre-interview survey results. The attributes that were deemed essential by half of forecasters, and I'm sorry you can't see the details here, but it's summarized in the words on the right. But you can see that the bars differ. So the orange ones all have to do with familiarization and training, and the blue ones all have to do with operational. And so you can see they're different lengths for some things. But some of these things were judged essential by at least half of the forecasters in both the familiarization and the operational context. Being able to compare the guidance with the observations. That seems like a no-brainer for anybody who's done forecasting. Knowing what the failure modes are, they really cared about. Knowing how the guidance verified, and there are a lot of specific kinds of verification statistics you can use. They have specific meteorological verification statistics they want to see, not just root mean squared error. And how it verifies compared to other guidance. Does it do as well or better than other kinds of guidance that is available to them? And they want to be able to interact with the guidance. This was very important to them, and to sample the product as well and know what the input variables are in both of those contexts. Specific to familiarization and training, all or most of the forecasters indicated that it was essential or useful to know why the guidance worked or failed, how the output was derived, and what data were used to train and calibrate the guidance, and finally examine the AI predictions for past cases. And then for the operational use, they thought it was essential or useful to be able to compare the forecast guidance to that of similar guidance valid at the same time. So they're making this trade-off decision between which tools to use, and to be able to examine the evolution of the guidance over time. So that's really important. So finally, for the content analysis, and here's an example of the kinds of information that we got, and in response to RQ1, how do they decide what model guidance and other tools to use? As a forecaster, you work in such an information-rich environment. You have a lot of tools and guidance at your fingertips. Why do you choose to use what you use? So this is this picture I was trying to paint for you earlier. Sometimes guidance may seem like a black box where you don't know how the output was derived. And to what extent do you need to know the details of how a product was derived in order to consider using it for forecasting? So just an example of the coding, this was new to our postdocs, and they found it kind of a nightmare. It took a long time for them to achieve a good level of reliability, intercoder reliability on these things, because it was an inductive approach. They built on Brown and Clark's work on thematic analysis. So But you can see here the kinds of inductive codes they came up with. People wanted a personal experience with the products. They wanted to understand this comparative performance, as we mentioned, and they were looking for records of model performance. And so performance, which is something that often comes up in context of AI, is it accurate? Is it making stuff up? Is it inaccurate? It was really important throughout, and that as we would expect it to be. So first on theme 1, forecasters want to understand to understand guidance to use it. And so what does it mean to understand what an AI model is doing? And there were a lot of different dimensions to this. And you can see a quote from Forecaster 11, you got to know how things are put together and how they're made to have a deeper understanding of what it's giving you and why it's giving you what it's doing. This is the ultimate black box problem of AI, actually. And theme 1.2, forecasters go through an iterative process of exploring and evaluating the guidance. So the interaction really facilitates that. So and this forecaster number 2 is talking about that and about how the study is done, but they really want to try stuff and iterate with the models. For research question 2, how do different descriptive and performance attributes developed using of prototype model guidance developed using AI influence forecasters' assessment of the guidance trustworthiness? And you can see that I'm going to talk a little bit about the impact of this initial background information for both of these. Theme 2.1, they apply their own mental models, their conceptual models of the atmosphere when they're initially making sense of the new guidance. The visual makes sense to me. This is what I would expect from a conceptual model of how I would expect the storm objects to evolve. This first image is something I would think that would be initially trustworthy based on what I've seen. There's nothing here that would set off any alarm bells that would make me think, oh, this literally doesn't have a clue what's going to happen. This being I think it was the convolutional neural network here. Theme 2.2, forecasters want additional baseline information about AI model development to better understand it. So they really wanted to hear more about the AI techniques, the model inputs, and how they're defined. And you can see a quote illustrating this here. So how do different descriptive performance attributes affect them? We also, after they'd seen this introductory information and before they'd gone through the information board, we asked them to rate from 0 to 10 how trustworthy guidance is based on the information provided. So it's a single question. And so we have their ratings on that. And then after the think aloud and after they worked through the information board, we asked them to do the same thing again. So we do have this quantitative, although relatively thin measure of their change. And what you can see here are the forecaster's guidance trustworthiness rankings before the think aloud, represented as a circle on the left there, and then the ranking after the informational slide deck and think aloud represented as a triangle. So all of the forecasters rank the guidance as moderate or high trustworthiness after working through this heavily curated informational deck. So remember that we based what was in this on our hypotheses from our initial work with the workshop, mostly. There are 3 here you'll notice that only have arrows and not circles, and that's because they deemed the background information insufficient to determine any level of trustworthiness. So they didn't want to give a rating at all. They basically refused to give a pre-workshop. And that's these 3 forecasters here. So how do they make these judgments? Well, here's an example of the sort of thing they said while they were doing the ratings. I don't know what went into the model necessarily, but what the synoptic conditions are, and I haven't had any experience with it up until this point either. So it'd be great. This is the pre-rating here. But I would want to verify it myself that it made sense with my conceptual model of what's going on. And then afterwards, I would go to 8 now. I'll just say I wouldn't completely trust it. I know that machine learning can get spurious results, but since I've only looked at basically 2 cases here, I don't have that long background experience information to bump it up higher. So knowing what's behind it and some of the verification, definitely somewhere between 7 and 8. But then I would need my own personal experience with it to trust it further. So these forecasters are definitely used to digging into the details of the model. They are professionals and see themselves as scientists in most cases as well. especially those with that level of experience. And so you can see here the overall results before and after the think aloud and the kinds of things that people nominated as or discussed went through and mentioned in their ratings of these, from not knowing enough about the model after just the background information to wanting additional background information and familiarity with the input data sources, being happy with the data sources, which are WARFN, href data sources in the after think aloud. You can see the kinds of things that they mentioned. So we got a good sense of what they were taking into account and what they took away from the informational deck as well in this context. And so we did ask people also if they'd want any more information. So they continue to want more hands-on experience with the guidance. And you can see a quote illustrating that here. It's got to be multiple cases that I've used myself to get my trustworthiness above whatever I call the standard or whatever my starting point was. So they really depend on being able to interact with the model. And they want to know how AI guidance and products will improve weather forecasting. What's the value added and then need being met? So one of the reasons I would argue that these two products in particular were rated as relatively trustworthy and valuable post information boards, they were meeting an unmet need. These products were in a forecasting area where their models were insufficient, the standard or conventional numerical weather models. So that's the whole picture of what we did, all thought through based on these really quite decades-old strategies for thinking about how to collect this kind of information. And overall, we concluded that it is a deliberative dynamic process, and they want iterative intentional engagements with the guidance to be able to judge trustworthiness. Now, in an environment where AI models are changing so rapidly, this is potentially problematic. And so we saw 3 phases in which forecasters evaluated the new guidance in different ways. First, their initial exposure and orientation to the new guidance, so that background information. Second, their further familiarization, where they were with new guidance through non-operational information seeking and interrogation. And then third, their operational experience through real-time observation of guidance and potential use of it for forecasting. So they had a little bit of interaction with a hypothetical case in the back information deck. These phases can overlap and are not necessarily linear. Each are a key part of the forecaster's assessments of trustworthiness. And as mentioned, this is going back to influence in theory that further prototype development. It certainly influenced our colleagues at the AI2ES when they saw all this. And more broadly, the forecasters really appreciated that we were taking this approach, that we were involving them in the development of the AI models. And so you can see this quote here. It's always nice when people working at national centers reach out to us. I think it makes it more trustworthy when a forecaster is using a product, if they know that, hey, other weather forecasting office people have given their input on this. So these highly trained professionals in another highly trained professional context value their input. So I'm just going to sum up here. I think I'm over time.
Okay.
I'll sum up. So I had just had a general we had some very specific hypotheses I mentioned from the workshop, and so I just want to give you a slightly different perspective on our overall takeaway. First of all, forecasters did not appear concerned about using AI or ML. They did not seem to have stigmatized the work. I think it's tremendously important. You know, it's the future. There's a lot of positive aspects. There was a little bit of concern about job security, frankly, that came up in some of the interviews, and that's been published in another paper that we have on this context. But that's as long as the guidance helps them forecast and communicate more effectively. So the performance really matters to them. Basically, any kind of technology that will help improve our forecasting capabilities, we really do want to message or forecast with confidence so that people will take action. So it does go to your public audience, George. And they talked about having to communicate. If you can't communicate it with the public, it's not very useful. So this ability to interact with the product increases trustworthiness tremendously. And so we had gone to great lengths to create these interactive interfaces for them to be able to do a little bit of interaction even in this with the prototype. And that's a stretch for prototype developers. And you see some examples here. And then finally, in another study, we found that, and also in these studies, if they knew that there had been hand labeling at some point, that increased their trustworthiness, as long as they had confidence that the hand labelers were actually experts and knew what they were doing. So that's really good information. I like it that it says trained by a human, especially when it comes to storm mode. It can be kind of tough, I think, to classify some of these storm modes sometimes. So it makes me a little more increase in tech. It's verbatim. Knowing that the data was used to train the CNN was based off something that was quality controlled by a human. So, so people were reassured by the influence of expert judgment in these contexts where they had confidence in the expertise. And it's important to think that to understand that mental models do play a role, that experts develop very specific mental models, and the more we understand about those mental models can help us better understand their reactions to AI in these contexts. They apply their meteorological conceptual model to make sense of the output. And I'm not going to read those quotes because I'm so over time, but this also illustrates the AI ML concept of local explainability through post and how people understand output through post-hoc methods for a given prediction. So that's the last part. We looked at AI predictive functions as a type of risk information used by professional decision makers to assess risks of weather hazards and make critical job-specific decisions. We found things at 3 scales in our work. The prototype scale, and I'm just repeat some of the findings here. Across prototypes and attributes, we found that model performance and input variables and being able to interact were super important. And overall, forecasters' trust in new AI guidance is a progressive dynamic process. It's not instantaneous, not maximized, and it's probably continuing to change because of the prevalence of AI. Trustworthiness we found stems from intersecting factors. Not written in this long list is that experts have very specific demands when it comes to things like verification. They have context-determined verification metrics that they want to use. And trust is inherently emotional and subjective. We saw this too, and this complicates efforts to calibrate trustworthiness in any regulatory sense. And to develop trustworthy AI, we need to follow that agenda that we laid out at the beginning of the talk. Thank you.